Methanoic acid, simplest carboxylic acid, occurs naturally, most notably in ant venom, has a molar mass 46.02. Use the values in the table below to calculate the enthalpy change of formation for methanoic acid. Well, there we've got 1 mole of methanoic acid and a half O2, but remember O2 in terms of formation is irrelevant as far as the energy needed for it. And over on the left hand side we have the elements in a standard state. There's a carbon, there's an H2 for the 2 hydrogens, there's an O2 for the 2 oxygens, plus of course that extra half O2 that we had on that side that means absolutely nothing. Now the reason why we had that extra half O2 is because these things here are combustions, and of course you need O2 to finish combustions. Okay, so therefore, going from here to here is delta HF, and we can go directly for delta HF, or we can combust the C and the H2, which we're told C is minus 394, H2 is minus 286. We get CO2 and H2O. Coming back down in this arrow, it's a combustion of HCOOH, okay, which is minus 263. So to get for delta H, we have to go either directly, or we can go around this little circle here. So we go first here, that's minus 394 and minus 286, and then we go back this way. Well, going back means we're going negative, so it's negative minus 263. Punch that in, and delta HF is minus 417 kilojoules per mole. Here we're given a couple of equations, right? Again, this was part 4, so I had to kind of put together some things. But anyway, the enthalpy change for reaction between calcium hydroxide and hydrochloric acid is minus 196 kilojoules per mole. Okay, well, got to write that equation out. This is a hydroxide, it's a base, reacted with HCl, so it's a neutralization. You should know this reaction, right? We get water, making 2 waters because we've got 2 H's and 2 OH's there, and then we make the calcium chlorides. Okay, next reaction, calcium oxide and hydrochloric acid. Well, let's think about that. Calcium oxide and hydrochloric acid, well, again, the H's are going to take the O's to make water, so you need 2 HCl, which gives you those 2 Cl's to go with the Ca, so CaCl2 as the products. And just to put in the energies of those, the first one, the gold reaction, minus 196, the blue reaction, minus 126.4. Now, various ways we could do this. We could set up a very convoluted cycle, but I like putting equations together, as we've seen in the videos, as we've seen several other places. So what we're going to do is we're going to somehow combine these equations to get this desired equation. So I'll start off with equation 1 because I want a calcium hydroxide on the left, and equation 1 has calcium hydroxide on the left. Okay, but now I've introduced calcium chloride on the right, and my desired equation does not have calcium chloride anywhere. So why don't I get rid of calcium chloride on the right? And the way I do that is I take an equation that's got calcium chloride on the left. Well, equation 2 has calcium chloride in it, but it's in the wrong direction, so I have to flip it. So when I take equation 2 and flip it, I get CaCl2 plus H2O now on the left, and CaO and 2HCl was on the left, now is on the right. Now when I add these equations together, the 2 HCl's cancel out on the left in equation 1, on the right in the flipped equation 2. The CaCl2's cancel out because that was how I did the thing. And then of the waters, one of the waters on the right up here cancels out with the water on the left here. So add that up and you've got the desired equation. Now, how do we get the energy for that? Well, equation 1 we just used as was. Equation 2, which was minus 126.4, but then we flipped it. When you flip an equation, you change the sign of the delta H. So add those together, and we get delta H minus 69.6. So we've seen 2 questions in which we're applying Hess's law, one of which was a little cycle, the other one of which was where we just add equations together. Now I want to look more formally in this next question at both of them. So we've got enthalpy change reaction, found indirectly, blah, 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 right? We use combustion. This is what we've seen all the way through. So let's start off with our equation we want. HCCH plus 2H2 goes to C2H6. Now we're told about combustions here. So H2, when you combust H2, use half an O2 to make H2O. When you combust ethine, that's that HC triple bond CH, then you make 2 CO2 because you've got 2 of the carbons. You make 1 H2O because you've got 2 hydrogens. Put it all together, you need 2.5 O2s. And when you combust ethane, which is C2H6, you're going to make 2 CO2s, 3 H2O, so you need 3.5 O2s. Okay. Now, what you're used to doing is you're just used to putting CO2 and H2O down here at the bottom of the triangle, drawing some arrows, and Bob's your uncle. I want to think about what we're doing here, because this equation right now has got absolutely nothing to do with combustion. But if we say combustion of HCCH requires 2.5 O2s, so we'll add 2.5 O2s, and now we can combust the HC triple bond CH. Combusting H2 requires a half O2, well, we've got 2 of those, so that's a half and a half. Now when we put all that together, we can combust it, we can write the combustion equation, okay, to make the 2 CO2s and 3 H2Os. That's the 2 CO2s with an H2O and then 2 more H2Os for the H2. Okay. Now, of course, by virtue of putting in 3.5 O2s on the left-hand side here, I have now not got a balanced equation. So what I'm going to have to do to balance it so that this still makes sense is I've got to add 3.5 O2s onto the right-hand side. 3.5 coming from 2.5 plus 1. Well, fortuitously, right, that 3.5 O2s is exactly what you need to combust C2H6. So now I can go from here down to that same combustion process. So I have created my little triangle, but I haven't just written it out, okay? I've actually thought about what do I have to do formally to be able to make this combustion circle, this combustion triangle. And the answer is you've actually got to remember and note that you're including the amount of oxygens needed on each side to make this correct. Now, of course, as far as this becoming delta H of the reaction, the 3.5 O2s and 3.5 O2s cancel out, so they don't affect the fact that the top equation is still delta H for this reaction. Anyway, now it's that nice little cycle, so we'll throw in the numbers. Combustion here, we've got a combustion of ethine, it's minus 1300, 2 of the combustions of H2, 2 times minus 286. Combustion here, going this direction, is of ethane, so that's minus 1600. But we want to go from here to there. Going directly is delta H. Going indirectly, with a nice little curly hand-drawn arrow, is by this combustion triangle. So delta H is going to be, on the left-hand side, going directly, is according to Hess's law the same as going around this circle. So around the circle, minus 1300 and 2 minus 286. But then we're going backwards here, so it becomes minus 1600. Pop that in, and we get minus 272 kilojoules per mole. Now, let's think about that in a much more formal sense. We have 3 equations here that have within them all the components of the overall equation we want. There's an ethine, there's H2s, there's an ethane. So what we're going to do is we're going to assign a little number to each of those equations just to help me label it. And I'm going to put together my equation here by combining some version of these equations. So the first thing I'll do is I say, well, I want 1 ethine on the left-hand side. Well, equation 2 gives me an ethine on the left-hand side as written. That's lovely. Now I've got some O2s and some CO2s and some H2Os, which of course are all over the place in all of these equations. So let's continue doing what I would like to think we're doing, build up the equation. We now need 2 H2s on the left-hand side. Well, equation 1 has an H2 on the left-hand side, so I can use that, but I'm going to need 2 of them. And when I take 2 of equation 1, I get 2H2 plus O2 goes to 2H2O. Again, I can see how my O2s are building up and my H2Os and CO2s are building up. Don't want to think about those yet, but I'll continue looking at what I want. I want a C2H6 on the right-hand side. Well, I've got equation 3 that has a C2H6, but it's got it on the left-hand side, so I need to flip equation 3. And when I do that, I get 2 CO2 and 3 H2Os are no longer on the right, they're on the left. C2H6 and 3.5 O2s no longer on the left, they're on the right. Now let's cancel some stuff out, shall we? I've got 2 CO2s on the right here and 2 CO2s on the left here. So when I add them up, the CO2s cancel out. Waters, I've got 3 total on the left, and I've got 2 plus 1 or 3. on the right, so those cancel out. O2s on the left, I've got 2.5 plus 1, so 3.5, which cancels out with a 3.5 on the right. Add all that together, and I do get my desired, very colourful overall equation. What do I do then with the delta H's? Well, just the same process we've used all the way through. Equation 2 I used as was, so that's minus 1300. Equation 1, minus 286, but then I doubled it. And equation 3, minus 1600, was then flipped, which means change the sign to plus 1600. Add all those up, and I get my same minus 272 kilojoules per mole. Two ways to think about it conceptually. This is one that's lovely for your whole combustion, which is what you've been practicing throughout your A-levels. Much better conceptually to think of it in terms of let's combine these overall reactions. Okay, very good question in the session about, well, how is it just fortuitous that they all balance out? And the answer is, well, yes, because this was an exam question set that way. If you go and look at some of my questions on the worksheet in particular, although also in the online quizzes for the thermochemistry module, you'll find quite a few examples of this, a couple of which where you're given extra redundant equations that you don't need to use. And of course, in real life, you would just have to think about what equations might I use, might I need the values for, and go and look them up. And of course, in this case, you just go look up a bunch of combustion values. Hopefully, it all made sense. So, same type of question, except now we're given combustions and then asked for heat of formation. Okay, so we want to use the data to get the standard enthalpy change for formation of ethanol. So it's a formation of ethanol. So we want 1 mole of ethanol as a product, and then we use the elements in the natural state as reactants. We need 2 carbons, we need 6 hydrogens or 3 H2s, we got 1 oxygen, so a half O2. Okay, so that is the heat of formation of ethanol. But we're going to use our combustion. So as we now know conceptually, we would add enough oxygens to the left-hand side so I can combust it and make my 2 CO2s and 3 H2Os. Okay, each carbon turning into a CO2, each H2 turning into 3 CO2s. Knowing, of course, there were extra carbons written on this side to make that true, we would have to add the same number of carbons on this side to make it true. And when we do, we can combust the ethanol to get the last side of the triangle. As usual, put in the numbers. We got 2 carbons, 3 H2s, so that's 2 times minus 394, 3 times minus 286, and over here combustion of ethanol minus 1371. We go around in that same, you might have noticed that same terribly drawly freehand arrow there, because I might as well, having drawn it badly once, just copy and paste it from then on. So the heat of formation going directly is going to be indirectly, 2 times minus 394, 3 times minus 286. That's there in the sort of browny bit. And then going backwards here, so minus 1371. Pop it in, you get minus 275 kilojoules per mole. Same old thing, okay, except now we're actually analysing it. Got standard length piece of combustion of carbon, hydrogen and ethanol. So that was that same question back there, just now continuing on. Okay, Amir said hydrogen's the best fuel of these in terms of energy released by burning equal masses. Well, let's burn a gram, shall we? Okay, if we burn a gram of carbon, it was 394 per mole. There are 12 grams in 1 mole, so per gram carbon gives us 32.8, right? Minus 394 divided by 12. Hydrogen, of course, we just got to divide by 2, so that's 143 kilojoules per gram. And ethanol, molar mass of ethanol is 46, so we get minus or 29.8 kilojoules per gram. Again, I'm being sloppy with my minuses, okay? But this is the amount of fuel, amount of energy you get out per gram. And so hydrogen significantly bigger than the other two. Thus, Amir is correct. Same kind of question, but with some added in concepts here. Charcoal is carbon, been produced many years by heating wood. Natural gas is methane, obtained from underground sources, forms similarly to coal and oil. Here are the enthalpy changes of combustion. Again, it is implied kilojoules per mole because these are the enthalpy changes of combustion by definition. So one said methane's more heat per gram, so it's a better fuel. Well, carbon has a molar mass of 12, so 32.8 kilojoules per gram. Methane has a molar mass of 16, so 55.6 kilojoules per gram. Thus, methane certainly does produce more heat per gram. So that's correct. Then the other student said, yes, but use of charcoal contributes less to the overall increased carbon dioxide levels in the atmosphere. Well, let's see, if you burn a carbon, you make a CO2. If you burn a methane, you make one CO2. Thus, the same amounts of CO2 are made, okay? But think about where these things came from. Methane is not renewable, okay? And so every single mole of CO2 that you make up there is going to just be there forever. Charcoal, on the other hand, is renewable from trees, okay? Trees grow. You cut them down, they grow again. You cut them down, they grow again. And of course, trees absorb CO2. So thus, as far as CO2 is concerned, charcoal is effectively neutral. So thus, charcoal is better in terms of the increase in CO2 levels in the atmosphere, and it is also renewable, although that wasn't actually really asked for there. And a nice little triangle here. Explosive RDX has this formula, so there's RDX. Use the data table on the Hess cycle to calculate the enthalpy of detonation, delta H, of RDX. So when we detonate it, it turns into CO, water, and nitrogen gas. Okay, so let's see what we've got here. Here are the elements in their natural state. Okay, solid carbon, H2 gas, N2 gas, and O2 gas. Okay, we go from elements in their solid state in this direction to make the C3H6N6O6. Then we are just essentially forming C3H6N6O6. So delta H1 is the heat of formation of RDX, right there. Heat of formation of RDX is plus 62. Now going in this direction, don't worry about the N2 because that's an element in its natural state, but we've got enough elements here to make 3 COs and 3 H2Os. Thus delta H2 is making 3 COs and 3 H2Os. So put those together and that's delta H2. So delta H1 go in that direction, forming 1 mole of RDX. Delta H2 going in this direction, forming 3 moles of CO and 3 moles of H2O. So put it all together, go directly, we get delta H. Go indirectly, we can have the same effect. Thus delta H is minus delta H1, because we're going backwards there, plus delta H2. Throw in the values, minus delta H1 is minus 62, and then we got 3 times minus 11, 3 times minus 242, and we have delta H of this reaction, rather big, minus 1100 kilojoules per mole. Explosives have very exothermic reactions like this, okay? That's why they're explosives, because you get lots of energy out.